Hi Year 12s, I'm just going to do a bit of an overview of using integration to find area. So the simplest sort are when we have a curve lying above the x-axis, okay, and we want to find an area between the curve and the x-axis. In this case, it's going from one root to the other root, so we can integrate. So we'd integrate from -1 up to 4 of the equation of the curve. So in this case, we've got this equation here. With respect to x. And so that would give us the region R. Okay, so we can always find the area between the curve or a line and the x-axis. So between an equation and the x-axis. Okay, then we met the case when we have a curve that lies below the x-axis, and if we did the integration this time, so I'll write down what it is. I don't know what A and B are at the minute, but we'll just write A and B. So this time our region goes from A to B. Okay, so whatever numbers those are, we'd put them there. And we have the equation of the curve down here. So x plus 1, x minus 5 with respect to x. So we'd work that out, and when we work that out, because it lies below the x-axis, we get a negative answer. But if the question was asking for the area, you would just remove the sign and give a positive answer. Okay. Now, because of that positive-negative issue, if we have to find a total area where some of the curve lies above the axis and some lies below, we can't just integrate it from the start to the finish. So I'm going to call this one A, this one B, and this one C. Okay, so if I wanted to find the area, I would need to integrate from A to B first of all, and there's my equation. And separately, I would work out the integral from B to C. Okay, so I'd do it for the negative bit separately, of x minus 2, x minus 5 with respect to x. Okay, and then you would take the positive versions of both of those. So I know that this one, being above the axis, will be positive. This one will give a negative answer. So if I took away that negative answer, then I get my total area. Okay, so there's another example here where it's not entirely enclosed. So you can see we're going from 0 to 1 for the positive bit and from 1 to 2 for the negative bit below the curve. But it's the same idea. Okay. Right, now that technique, just finding the area between a curve and the x-axis, means we can find all sorts of areas. So here we've got a strange one. So I've got two different curves, and part of the puzzle is to work out which is which. Now you can sketch them on your calculator, okay, and it turns out that this one is y equals 6x to the 3 over 2, and this one is y equals 8 over x squared take away 2. Okay, so if I want to find out the area between the curve, which curve? And hopefully you can see that we've got the first curve just going from here to here, and the second curve going from here to there. So let me call this A and this B. So if I wanted the total area, I would do it in two stages. I would have this bit, and I'd add on this bit. Okay, so either the question will tell us that they meet at a point, which it does here. It's hard to see there, sorry, 1, 6. Okay, or part of the question would be to find that point. So if I want the total area, then I would be integrating from 0 to A, 6x I'd be integrating from 0 to a 6x to the 3 over 2 with respect to x, and adding on from a to b 8 over x squared minus 2. Okay, so that's gone a bit fuzzy. There we go. Hopefully you can see that. So this is this area, this is that area. They're both above the x-axis, so they're both going to be positive. Okay. Right, then you can also find areas that are kind of floating in midair. Now we can only find the area between a curve and the x-axis. So here I'd be interested in using the area between this curve and the x-axis, which I know how to find. So to find that total area, so I'm going to just put it in red, okay, and I'll call that, so that's R, so I'll call this S, the big one. So that total area here, we would have S is the integral. I don't know what these numbers are, but they relate to A and B. So I'll put AX and BX. Okay, so I'd integrate from the lower limit AX up to BX. Okay, and I'll be integrating this curve, which in the question it tells us it is minus 2x squared plus 4x with respect to x. Okay, but that gives me the whole shape. So then I'd want to take off this bit that's only red and not red and black, so that I'm left with the black bit. So I'm doing the whole kind of cake shape, take away the rectangle, will leave me with that kind of floating segment shape. Okay, so for this I could integrate this horizontal line, which is y equals 3 over 2 from here to here, or I can just find the area of the rectangle. So I'd find the distance and times it by the height, and then I'm doing the integration for the curve, take away the base times the height, and that leaves me with what I want. The other approach to that is to do it all in a oneer. So we've got, this is y is minus 2x squared plus 4x, and the lower curve is y equals 3 over 2. Right, so if I want to do it in one go, then what I could do is I could say that kind of floating shape is going to equal the integral from ax to bx of the top one minus the bottom one with respect to x. Okay, so the top equation, this obviously it's a bit more in focus, there we go. The top equation was the minus 2x squared plus 4x, and then the bottom equation is y equals 3 over 2. Okay, so that would do the same as if you did the integral for just the curve, take away the rectangle, it gives you the same answer. So let's have a look at another question that's similar. So there's several ones that we can do like this. Okay, so here we want this bit, that's not between the curve and the x-axis, it's above, which is a bit useless, isn't it? But we could use the area between the curve and the x-axis, and we could work out the area of the rectangle, and we can find the difference. Okay, so we could do rectangle minus the curve, and that would give us the bit we're after. Okay, right, and so you'd use these as your limits. It says the x-coordinate of P is 2, so we know that's 2. So to find the area of the rectangle, we do 2 times n. And then we're taking away the integral from 0 to 2, and it's this equation, so x cubed minus 10x squared plus kx. That's the equation of this curve. That's it, and that would work out our answer. The other way to do it is we know that this equation is y equals n. So we could do it all in one go, the integral top minus bottom. Okay, so that would give us from 0 to 2, y equals n, take away, and then we've got three terms here, so we need brackets. So we've got x cubed minus 10x squared plus kx with respect to x. Okay, and then the other fancy sort that we get are ones where we don't have a nice horizontal line or rectangle, but actually we've got a diagonal line here. Okay, now we're given the equation of this line and the equation of that line, and again it's floating in midair. But if we draw down to the x-axis, okay, and I think that's it, we know that this would be ax again, and this would be bx. Okay, we could do the whole area of the trapezium and take away the area under the curve. All right, so we can go trapezium minus area under curve will give us the floating area that we want. All right, so you'd have to remember that you add the parallel sides, halve it, and times by the perpendicular distance, or you can do it in a 1-er where we do the integral of the top equation minus the bottom equation. Okay, so let's have a look at that one. If we did that, we'd be integrating from ax, whatever that is, to bx, and the top equation is 3x plus 20. And the bottom equation is the quadratic. So it's got several terms, so I'm putting them in brackets so I don't mess up the signs. Okay, and that would work out the shaded area that we want. Okay, I think there's one other type to show you which is a bit strange. So if we look at this curve here, it looks like it's an area between two different things, but actually if you chop it here, you can just split it into this nice curved area. So let's call that, there we go, call that AX. So going from 0 to AX of the curve, which is a cubic. Okay, and then we take we add on this triangle. Okay, and you just add the two areas separately. So if the shape is kind of looking like it changes going along the way, you split it into pieces, just like we did with the some above the curve, some below the curve ones. Okay, so it looks different. We split it into pieces. But when you've got some floating in the air, okay, or kind of above rather than close to the axis, then you split it in vertical pieces, well, whole pieces. You take whole pieces and take the whole away. So an entire piece and take away the whole. Okay, I hope that's helped.